I don't know.
That way it's interesting. Should we just like assign this and assign this and then for like lecture, she should really just go on side.
All right, it's time for us to get started. A couple announcements before we do. We will have a study session on Thursday. I don't know exactly. Hopefully people have questions. I won't have anything planned to go over on Thursday, so please bring your questions about the study guide. Is there anything that I can clarify from the study guide ahead of Friday's exam that would help you to study?
If there's an example of the app before, like an actual chunk of code, that could be.
Yeah,
That would be.
I'll try to bring that on Thursday so that we can take a look at exactly how that before works and runs. Right. Anything else? Excuse me. Slowly improving on the bronchitis, slowly getting back to normal. Who knows? Sometimes that lingers for weeks. So maybe this will just be a really fun quarter. Last time we started very briefly talking about UML. Today we're going to take a deep dive into it to make sure that this starts to make sense. We need some way of communicating and visualizing our code designs so that we can communicate with people who aren't as technical as us, or who are as technical as us and maybe have different terms for things. Or we have a very large project and we want to make sure that we're developing the same thing as the rest of our teammates, coworkers. So we talked about this. We're going to dive into a incredibly brief. I don't usually think the history is super worth going into, but just giving you a very brief idea of the associated decades of some of these things happening. So OOP, object-oriented programming, became prominent in the 80s. So we needed some way of creating a modeling language, a way to model the class structure, because this is so different from procedural code. When you can make objects and relationships between objects, we need some way of communicating that. So by the early 90s, a lot of people had come up with a lot of ideas. There were over 50 object-oriented modeling languages, and that's obviously not great. You draw something in one modeling language and another person says, I've never seen that before. I use these other 6. So in the 90s, the leading object-oriented notations decide to combine and produce some kind of desire to set some kind of industry standard so that we all communicate using the same modeling language. We could all communicate with each other. So from this was born UML. So UML is definitely not perfect because it was designed not by an individual or by an expert. It was designed by committee, basically. We had a lot of people trying to push their individual modeling language to make it part of UML. So everyone wanted their voice to be heard. So you could really just call it the union of all modeling languages rather than the unified. I don't know if unified is really the right word for it. It's really just a bunch of modeling languages put into a blender. Sorry again. So the resulting design is really, really big. There are lots of different kinds of diagrams, lots of styles that are all worked together. So it's worth just kind of breaking this apart as much as we can, and we're going to cover as much of this as we reasonably can. So we're going to discuss different kinds of diagrams. We'll discuss use case diagrams, class diagrams, object diagrams, sequence diagrams, activity diagrams, and state diagrams, all of which communicate somewhat different things. For the sake of this class, class diagrams are going to be what I spend most of the time on because it is what's going to help you to best understand design patterns. But as you move forward in the software engineering track, you will start using use case diagrams, sequence diagrams, activity diagrams as you start getting involved in courses like software engineering or your capstone. Even all of this, just a subset of UML, there's so much more out there to learn and know. It's a lot. It's not something that would be very fun to cover in a classroom setting, and it's usually something that you want to see and then very quickly apply. So rather than have an entire UML course where we just go over all of these kinds of diagrams, I like to try to keep it to a week at most. We'll probably be able to cover this within a couple of days. It's important, but more so important that you see it before you start to use it. And again, as mentioned, the class diagrams and object diagrams are the most useful with regards to understanding design patterns, which will be useful for this class. So let's talk about the first one, a use case diagram. So we want to be able to represent actors who use or utilize a system. Use cases, why would somebody use this system? And then the relations between these actors and those use cases. So the goal is to show how different subsystems in a larger system interact and who is responsible for which aspects of this. So think of it like actors are frequently humans. Humans use systems, and we want to be able to do something like draw a diagram for how a restaurant is operated. So here's the use case diagram. We have some actors. We have 4 actors in this system. We have the client who is ordering food or drink. We have the waiter who is doing what a waiter does, take their order, ensure that the order is delivered to the correct table. The cashier who makes sure that things are paid for, and the chef who actually produces the food. These are the 4 actors of the system as a whole. So we're going to want to figure out, okay, how do we design this system if we were going to be doing this and writing the associated code where each one of these circles is some kind of process. Note that we're not defining at all what that process looks like in a use case diagram. We're just saying this process exists, and also which actors are responsible for which aspects. So for instance, the client places an order in order to order food, but that affects more than just that one actor in this system. The client and the waiter are having an interaction through this ordering food system. So from the client's perspective, they place the order, and from the waiter's perspective, they receive the order, but they're both interacting with the same idea of ordering food. So they're interacting with each other, and we can see that in the diagram. The waiter has some other responsibilities besides that. The waiter needs to, once the food is ready, serve the food, and it needs to facilitate the payment of the food. It needs to bring you the check and take away the payment to be ready to be processed. It's not the cashier who comes and does that, that is the waiter who goes and does that. So we need some way, imagine that you had no idea what a restaurant was. We would need some way to show how a restaurant works and operates and who is responsible for what. So a use case diagram looks exactly like that. We're explaining the system in terms of who is responsible for what. We're not talking about how, it's more just who. Who and what. Questions on this diagram at all? Does this make sense? Do you feel like you understand, if you were one of these actors, that you would understand what responsibilities you have? Again, it's not how to do those responsibilities. This is not an instruction list, but it's more so who is responsible for what.
So with the line, you have a bunch of arrows, as to, you know, they can be extend.
Yeah,
Would arrows be useful in any other spot here, or the connections, or kind of connect them?
we're just we're showing that they're related. And we'll talk about different relationships and relationship types in a moment. These are in such a way that they're just kind of generic relationships. We know that these are related, but we're not further defining how they are related. In this case, we do have kind of an extends relationship between eating food and drinking wine, because the way that food is handled is basically the same as the way that wine is handled. So we can say that we can extend drink wine to be like whatever needs to be done for food that also needs to be done for wine, the exception of gets cooked. Yeah, that's a great question though. Other questions about this diagram? Not that I get this wrong, no. Okay, so we're going to define this system a project and resource management system. At the most basic level, a resource manager manages resources. Great, obvious, it's almost in the title itself. A project manager manages projects. A sysadmin is responsible for administrating the system. A backup system will house the backup data for the system. Imagine drawing a very high level use case diagram that represents this system. It could be something just as simple as this. So we see that we have actors, we have stuff that the actors do, but there's very much, this is extremely high level. This can be useful because we can write another use case diagram that zooms in on any one of these and further explains exactly the components of this system. So you can have different use case diagrams at different levels of abstraction that help you to understand how the system works. You have a very high level system, and then you have another diagram that explains each one of these components of this system. So let's zoom in on the project manager, this middle project manager and manage projects. What does that look like? Well, sorry. A project manager can add a project, remove a project, update a project. Removing and updating projects requires you to locate said project. Updating a project could involve adding, removing, or updating an activity or a task, or assigning a resource to a task, or unassigning a resource from a task. And this is what's necessary in order to manage a project. So while we had this project manager manages projects, if we were to zoom in on that, we might get something that looks something like this. A project manager now manages projects in ways that are much more concrete. But now imagine trying to shove all of this into the prior use case diagram. It would get really busy, and it would be difficult to see what the project manager is responsible for versus, for instance, the system administrator. It'd be really difficult because they don't all be crammed into the same diagram. So we can have different levels of this to be able to show who's responsible for what at a high level and at a little bit of a lower level. So now we can see exactly how this is done. Like update a project extends there's a bunch of subclasses behind update the project, because updating a project is a generic idea. That doesn't tell us exactly what we need to do, but updating a project may involve assigning a resource to a task, for instance. So there'd be a natural inheritance hierarchy for that. And now we can see that update project can involve lots of different subtasks. Gives us a little bit of a sense of what the code structure for that might look like. So we can start to think at different levels of abstraction. Questions about that? All right, time to get into the real meat of what's going to be useful for this class. Class diagrams. we're going to be describing classes in the object-oriented sense. So that means a class is not what it does. We have the name of the class, we have the fields of the class, and we have the methods of the class broken down into the associated sections. Name, fields, methods. And note that this looks very much like an interface. We don't know exactly how stop train works. We're just telling us that there's a stop train method that is part of this object. So as mentioned, class diagrams are static. We know what interacts, but not what happens when they do interact. So each box is a class, you'll list the fields, you'll list the methods, and that tells you what a train contains. We know its fields, we know its methods, we know its state, we know its behavior. So we have multiple class diagrams. How do we show how objects relate to other objects? Because that's a very important part of computer science, right? We write these objects and they interact with each other to create behavior that does what a client wants us to do for them. So let's talk about all the different relationship types that we can have between these class objects and what those need. Lots of possible relationships. It's very nice to be able to, let's say we want to talk about the strategy design pattern. We would need to know how those classes relate to each other. We can talk about the example that we went over last time where we had characters and weapon behaviors and we had the associated relationships between those. If we draw the arrows a little bit differently, we can see what kinds of relationships exist between these classes in a way that tells us how they interact and what the overall project does without needing to dive into any code whatsoever. So we can have two different kinds of association, directed or undirected. We'll talk about each of these in more detail. There's a slide for each of them. Reflexive association, multiplicity, aggregation, composition, generalization, and realization. These are the big, important ones. All right, association can either be directed or undirected. If it is undirected, it just says these are related, but not in a specific way that could be defined by any of the other types of relationship arrows. So it's not an inheritance relationship. It's not realization. It's not any of these other types, but they're related. There are methods that involve communication between these objects. An example of this might be something like an airplane passenger and the airline of the plane that you're flying. There is a relationship when you bought the ticket, maybe you bought it through the site of the airline and the airline is responsible for overseeing hiring the pilot, making sure that the plane has, there's something there, but it's not easily quantifiable as to what is the relationship between a person flying an airplane, being a passenger on an airplane, and the airline that's responsible for that flight. So we just draw this as a connection. It's just a line between these two class objects. If it's a high-level use case, then we're just going to have the name of the class. But these also may be class diagrams where the airplane passenger and the airline each further have the list of fields and methods associated with those objects. Those are both perfectly fine, and the relationship arrows work for different kinds of UML. So it's kind of a generic, how do you show that two classes are related in an unspecified way? We use association, just draw a line between the class boxes. One thing to note is that this is undirected association. Does it make sense for there to be a directed association here? Does it make sense to go from airplane passenger to airline? Or from airline to airplane passenger? Is there a direction associated with the flow of this relationship? Not really. They're related, but it's not really a flow from one side to the other. If there is a flow from one side to the other, what you have is called directed association. So there is some kind of directionality to the relationship. It's not just they're related, but think of it like airplane to passengers. So you're a passenger on a particular airplane. An airplane houses a list of passengers. So usually what we have, we call it a container and containees. So we want to draw an arrow from the container to the containee. So we get something that looks like this, where we have an airplane that contains passengers, and we have an arrow drawing toward. Note that this is a filled triangle arrow between airplane and passenger. So that represents directed association.
Does it have to be that direction, so the arrow is,
From the container to the containee.
that's it, okay.
Yeah.
No matter what direction have it going.
Right, if we flipped passenger to airplane, then the direction would also switch.
Okay.
We just want to make sure it's going from airplane to passenger. Reflexive association is a little bit different. A class can have multiple different functions or responsibilities. That just means that depending on who that class is interacting with, maybe the class takes on more of a leadership role or more of a following role. It's not easy to dictate exactly how this class relates to other classes. You can think of this like maybe we have an airline staff member class. A staff member may be generalized to be a pilot or an aviation engineer or a ticket dispatcher or a guard or a maintenance crew member. Those are all airline staff members. And the associated relationships that those have with other things might be a bit more complicated. We can have a relationship within that same class. For instance, maybe the aviation engineer and the pilot communicate in some way, shape, or form. Or the maintenance crew member and the guard are going to communicate with each other about their associated schedule. So reflexive association is a relationship from a class to itself in such a way that possibly different instantiations of this class may have that relationship. This necessitates talking about the cardinality of that relationship. So how many objects of each type are there on the from side and the to side? So we can use something like 0 dot dot star to say something like 0 or more, saying that maybe this doesn't actually exist. Maybe this relationship does not exist. But if it does, then something. It allows us to be very uncertain about the relationship. So now we have, between an airline staff, we have an association between the class and itself. Note it's not directional, but even if it were, it would kind of work that way regardless. The arrow wouldn't really have a from and a to. But this 0 dot dot star says that some airline staff may have some relationship to some other airline staff in a way that we're not really specifying here, but it would be a way of saying something like the maintenance crew member maintains the guard, or the guard maintains the maintenance crew member, or some kind of relationship between instantiations of this class. So we call that reflexive association. Questions on anything related to association? Those are the 3 different kinds of association. All right, next we'll talk about multiplicity. So we can communicate more than just the relationship. We can express how many of each are related. So for instance, like a car has 4 wheels. So you could have a multiplicity relationship of 1 to 4 of the car class to the wheels class. Another example might be the airplane to its passengers. We know that an airplane does not need any passengers in order to fly. It needs a pilot, but it doesn't necessarily need any passengers. Maybe it's just a cargo plane. If we're working with some kind of abstract class, we don't really know an upper limit to the number of passengers that an airplane could have. Maybe it's a really large airplane and can have hundreds of passengers. So we can now say something like, there are 0 or more passengers in an airplane. So we can communicate that cardinality in a way that tells us exactly how many of one class are related to another class in some way, shape, or form. Questions on multiplicity? All right, now it gets slightly challenging. We're going to introduce 2 of them at the same time because they're frequently confused. Aggregation and composition. Have we heard of these before and know the difference between them? Does anyone know the difference between aggregation and composition off the top of your head? Then it's very good we're covering this. So we know that one class belongs to a collection in both. In aggregation, we have this concept of shared ownership. An object can exist in more than one collection at the same time. It also means that there's no ownership implied between the collection and the element of the collection. We'll see a couple examples of this momentarily, but it means that there's not direct ownership. That's the way that I like to think about the difference. Ownership is the clearest way to see the difference between aggregation and composition. So there's going to be a hollow diamond on the contains side of the aggregation. Composition, on the other hand, is going to start out looking exactly the same. One class still belongs to a collection, thus the confusion between the two, but no sharing is allowed. If an element of this collection exists, then it cannot belong to another collection at the same time. So it's a very strong has-a relationship and implies ownership. If you're writing a composition, then there is a filled diamond on the contains side. We ready for some examples? So think about ownership. Ownership usually tells us the very easy way to distinguish between aggregation and composition. So here is our first example. One of these is aggregation, one of these is composition. We have a car to its wheels and a project to 1 or more consultants. Which one of these is aggregation? Which one of them is composition? Where does the hollow diamond go? And where does the filled diamond go?
Composition would be like the project. And then aggregation would be the car. Because other things, other than a car, could have wheels.
Interesting. Let's see if I can clarify this. Can a wheel belong to multiple cars at the same time?
A single wheel?
A single wheel by
No,
multiple cars at the same time.
no, you have the different wheels per car.
Can a project have multiple different consultants at the same time?
Yes.
Yes. So that's what's gonna differentiate kind of the ownership. Does a car own its wheels? Yes, if you remove the wheels, then the car doesn't really function anymore. You can't have a wheel that's simultaneously on your car and on my car at the same time. So there is strong ownership implied by the car to its wheels, and there is not strong ownership implied by a project and its consultant or consultants.
Would it be correct to say that a consultant could work on multiple projects at one time as well?
Yeah.
Or is that breaking this?
No, that works exactly, that's exactly right. So the composition is on the left and the aggregation is on the right. Now the question is, where do the diamonds go? On the contains side is where they go. So what is the container in each of these cases? The car is a container, is the project or the consultant a container?
The project.
The project. So yes, here we go. So that completes the relationship between these associated structures. Ready for the next one? Wait. Is frequently confused.
Want a beach or is it just?
Wait.
Now I'm not specifying.
Would it be aggregation on the left and composition on the right?
That is correct. Why?
Because the students, they're used in many other courses or classrooms. Where
Yeah.
in a CAT building, you can't move the classroom itself.
Yeah, if the left were composition, you would take this class and would not be allowed to take any other class at the same time. Sorry. Yeah, it's gonna take you 12 years to graduate, but that's just the price of being in a composition major. So when whenever one of your music friends says, yeah, I'm majoring in composition, laugh at them. I'm sorry, it's gonna take you 12 years to graduate. You're taking multiple classes at the same time? No, you're taking an aggregation major. You're getting this completely confused. On the other hand, does this building own its classroom? Would it be possible for this classroom to be part of multiple buildings at the same time?
No, and if you could, it'd be a weird hate to wall for your one.
That would be really strange for this exact classroom to also exist in some other building downtown. We'd have to invent teleportation or some kind of, it just stops making sense very quickly. If you think about ownership, this class does not own its students, but the building absolutely owns its classroom. So I find that ownership very much helps to clarify where this is. What is the container again in each one of these examples?
Classroom.
Yeah, the stuff that's on top of it. So the classroom is the container for its students. The building is the container for its classrooms.
Wait, the diamond thing goes on the teeter side.
Yes, the contains side. Let's take a look at how this would look a little bit in kind of some generic code. Say, what is the difference between aggregation and composition when you're writing a program? Let's say we're writing a car class. We have composition here on the left, and we have aggregation here on the right. Why does this make sense? From what we know about composition, what about the code on the left tells us that this is composition? And from what we know about aggregation, why do we know that what's on the right is aggregation? What is the difference between these two implementations?
You're taking into consideration like specific aspects of that car's engine.
Yeah.
Yeah, but that's not engine on, right?
Yeah. What about the difference between the engine fields? What's the difference between them? Composition is final. When we construct the car, the engine goes in the car, and there is an engine that is associated with this car. We are not going to remove this engine for any reason. We can't swap it out, which implies ownership. The car on the left owns its engine. The car on the right does not, and we could swap it out. Because we could swap it out, what do we have to do? What do we have to check before we just tell the engine, do your thing, make the car go vroom? Because we can swap out the engine, that means the car can exist without an engine. So we need to check, does it have an engine before we try to say, engine go vroom? If we try to say engine go vroom and it does not have an engine, we will get a null pointer exception. So we need to check for null in advance. When we construct the car, we have a set engine on the right that allows us to pass in an engine to associate an engine with a car. On the left, there's no way to pass an engine in. We are going to make it part of the constructor, that we make an engine and then associate that engine and only that engine with this car. So very big differences in terms of what you can do and the ownership that is implied between the composition style car and the aggregation style car. Questions about the difference between composition and aggregation? Very frequently confused, think ownership and a little bit of multiplicity. Can an engine be used by multiple cars? On the right, yes. You swap it out, put it in another car, and it just works in the other car. On the left, we cannot do that.
Wait, wouldn't you want to not share engines with cars? Because there'd be lots of problems in doing so.
We're not making any statement or claim about which one is correct here. It's just the idea is you could design a car in either way. You could design a car where we have composition between it and the engine, and we could design a car where we have aggregation between it and the engine. And that's a design decision that we would make when we make a car object and an engine object.
Wait, so what the left is
Composition. For inheritance, we use the term generalization, which makes sense. An abstract class is a generalization of a concrete class. An interface is a generalization of a concrete class. So this gives us the inheritance relationship. So we're going to have an open triangle on the abstract class, and we are going to have nothing on the concrete class. But it gives us kind of directionality that says that the button is the abstract class and the request button and the emergency button are the concrete classes. So again, open triangle gives us inheritance. We'll call it generalization. We can have multi-layered generalization, where now we have an abstract class doctor that has subclasses, hospital doctor and general practitioner. General practitioner is a concrete class, but hospital doctor is another abstract class because it has an extension down into cardiologist. So each one specifies a superclass, subclass relationship. The last one we are going to talk about is realization. And we have realization whenever we have two classes and one class defines the functionality of the other class. So an example that we use for this is something like Imagine that we have a class that contains all of the instructions for setting up a printer. And then we have another class that is the use of said printer. Can we use a printer before we set it up? No. So we have a realization requirement or relationship between these two classes, where in order to do anything with the printer class, we have to have gone through the printer setup class. The way we're going to show it is with a broken line with an open triangle, so it looks kind of like generalization, except that instead of a straight line, we're going to have a dashed or broken line. So we get something like this, where in order to use the printer, we have to have gone through the printer setup. So these are the important relationships that we can know between classes. Very important to know the difference between these, because it's going to be very useful when we go to do something like look at the strategy design pattern. And in fact, I'm going to go do that right now. Oh, bad email. This is a site that everyone should get familiar with. Refactoring.guru. You're going to be using it a lot in this course. One of the aspects of Refactoring Guru is an entire list of design patterns. This is a phenomenal resource as you are learning design patterns and implementing design patterns to make sure that you can understand them. So here's the strategy design pattern. You can read all about it. The intent of the pattern: define a family of algorithms, put each of them into a separate class, make their objects interchangeable. That sounds like exactly what we did with the duck pond example.
Wait, this is free, right?
Yes, this is just go to refactoring.guru.
Oh,
And
good.
the entire site is amazing. There is a paid design patterns book here that you could purchase, but it's just all of the content that is already free online. Very useful resource. It defines the problem. What could cause you to want to apply this design pattern? It gives you a solution. How do we get around that? But now we start seeing UML diagrams that tell you what are the associated classes. If you were to go write your own strategy design pattern, you would want to build something that looked like this. In order to be able to understand all of these boxes and arrows and diamonds, we need to have an understanding of UML. You can see in general, we have the client interacting via realization with concrete strategies, which has, sorry, that's the realization of a strategy. And then we have a hollow diamond, so we have an aggregation of context and strategy. But then we have the arrow representing that there is composition, that one is composed of the other. A strategy is an element of the context, which you see, it's one of the fields here. The dash represents a field, the plus represents a method. So there's a field of a context that is a strategy, so that we see that there is a relationship, a composition relationship here that says this has that as a field. And then the hollow diamond says that as well. So we can start learning to read these kinds of diagrams that tell us how to actually implement this in code form. Other things to know about Refactoring Guru: they then give you pseudocode for their example. So they give you some example in the problem and solution, and then they're going to go through exactly the pseudocode for it. And then the really important part for you, as you scroll down even more past the frequently asked questions or the applicability and the how to implement and some pros and cons, and some relationships with other design patterns. All the way down here at the very bottom, code examples in a bunch of different languages. These are all clickable. If you go to the Java button, you can see a full code example of different payment strategies. This would allow you to build a site that then when the user went to go pay, you could have the swappable, they could choose how they want to pay. Pay by card, pay by PayPal, pay by Venmo. So here is the entire code for exactly what this would look like. So this is extremely good resource for figuring out, okay, I understand this strategy design pattern at a very high level, but what does the actual code for this look like? I have not had a chance to scrap all of what I think are kind of garbage labs for this class. So what I give you will be very much like a code to the API like you've seen in 210 and 211. I'm not very happy with this. I've made a project, but I have not had time to fully go through and make a lab that's something like, makes something exactly like this. So that means that you're probably going to have some gap after doing these labs of how do I actually go implement this, and trying to go from filling out an API related lab to the project, which is going to say, take multiple of these design patterns that we have seen and write a program that incorporates all of these design patterns. A lot of the learning for that is going to be embedded in this Refactoring Guru site, analyzing this code, understanding how the design pattern works at a code level. So I just want to be very upfront about that there's going to be a little bit of work to do between the submitting the lab and working on the project. And this is a phenomenal resource as you are working on your project for understanding every design pattern that we're going to cover. And I will probably be referring to the site significantly over the course of many of our lectures because it's just that good. There is no better resource that I am aware of for learning and seeing design patterns in action than Refactoring Guru. I think this is one of the links and tools on our Canvas. If it is not, then it should be, and I'll make sure that it gets up because it's incredibly useful. All right. So here is a project class diagram. We can see that there are associated classes, project, activity, task, and resource. And now we can start seeing that there are relationships associated with these different classes. We can see there's multiplicity. A task is assigned to a resource, but there could be an arbitrary number of tasks assigned to a particular resource. So that's just what star means in this case. That's a 0 ... star from before. There could be no tasks assigned to a single resource, or there could be an arbitrary number of them. There's nothing that says that there can't be 28 tasks assigned to a particular resource. But for each activity, there are multiple tasks. For each project, there could be multiple activities. So this is high level. If we wanted to say what do each of these classes actually contain inside of them, we could do that. Now we've broken down each of these classes into their associated fields and methods. So a project has 3 fields: names, description, and start date, and then a bunch of methods. What can we do to a project? We can create a project, set the name of a project, get the name of a project, set the description of a project, get the description of a project. So this is a much more detailed class diagram than just the very high level one. And we can start to see what are the components of this. Imagine handing this to one of your friends who is also a computer science major. Would they be able to implement this particular class structure? Again, we're not talking about any of the logic inside any of these methods, but would the correct fields and methods be in each class? would those classes have the appropriate relationships with each other? They would, just by drawing out this one diagram. This becomes a great way to communicate within your group what the overall code structure should look like without actually writing any code yet. So we'll come back to this and finish up UML related stuff probably tomorrow. But this was a good start. Let me know if you have any questions, and I will have an hour of office hours in my office starting right now.
So for the exam on Friday, I'll actually be in Florida.